Okay, so what we've done so far is we've kind of been introduced to functions of several variables. Instead of just having one independent variable, we have two or three. That's what we've been looking at. Now we're going to, you know, like before you took Cal 1, you studied functions. Now we've got multivariable functions. Then in Cal 1, the first thing you did was talk about limits. Now, really, and so we're going to revisit that with multivariable functions. Now, really, I think you could call calculus the subject limits because everything you do in calculus is based on limits. We define the derivative with the limits of a difference quotient. We define the integral with the limit of Riemann sums. In Cal 2, we talked about limits involving convergence of series. So we're talking about limits all the time. And here we are with limits again with these multivariable functions. Now, what I want to do is just refresh your memory about limits, what limits are in the two dimensions. So remember, we had this. We had the limit as x goes to a of f of x equals L. And we just need to have a thorough understanding of about exactly what that means. That doesn't mean, you know, it has a rigorous meaning. It's not just that you can plug in or we get closer to some value as x gets closer to a. I mean, that we want to look at it a little more rigorously than that. Okay, so what we say is this: we look at pictures like this. We consider a function like this. Here's a function. Let's suppose this is f of x. Now remember, and let's suppose this down here is a, and over here is L. Now, when we say that, here's what we mean. And I realize this is review because, y'all are in Cal 3 now, but for let's just consider this part here. This is L plus epsilon, and this down here is L minus epsilon. In other words, this little distance here is epsilon. And then you notice that we can go over and down like that, okay? Now, when we talk about the limit as x goes to a of f of x equals L, what we mean is this. No matter how I box in L, no matter what I choose for epsilon, however small it is, I can always trace back down and find a boxing in of A so that let me show you. I can always trace back down. Let me do a different color. I can always, let's suppose that, see, I've got this width here, and I've got this smaller width here. I'm going to call that delta. Okay, so I've got A plus delta and A minus delta. Now notice what I did. I just said, okay, let's box in L with an epsilon plus epsilon minus epsilon, and then let's trace it back down to the x-axis and box in A. Now notice this, that no matter what, in this little pink stuff that I put here, no matter what value for x I choose, it's going to have a function value within L minus epsilon and L plus epsilon. In other words, no matter what value I choose down here, it's going to have a corresponding y value between L plus epsilon and L minus epsilon, no matter how small I make epsilon. That's what we mean by limits. So we say this: for all epsilon greater than 0, there exists a delta greater than 0 such that if this is true, if this, then this. And there you go. Okay, for all epsilon, no matter what epsilon you choose, I can find a delta that boxes in the a, so that the distance between x and a, if it's less than delta, then I'm guaranteed that that will correspond to a function up on the vertical. So no matter what epsilon neighborhood I choose, I can find a delta neighborhood. Okay. So, and all this, any questions about that? Now, so that's just a reminder about what we mean by this limit. Now, also remember this, that in Cal 1, back then we limited ourselves to one independent variable. Remember, we had situations like this. We had A here, and let's look up here. Here maybe we'll have that, and we'll have this, okay? And maybe this one right here corresponds to 3, and this one up here maybe corresponds to 5. Remember, we said this. We would say the limit as x goes to a from the right is equal to 5, while the limit as x goes to a from the left is 3. See? So we had a jump in the graph like that. So we would say the limit as x goes to a does not exist, because it doesn't make sense to say, okay, what does f of x get close to as x gets close to a? Well, it depends. It depends on the direction. If you're coming from over here, you get one thing. If you're coming from over here, you get another thing. So we can talk about the right-hand limit and the left-hand limit, but the limit itself, well, and if you try to, like if I give you an epsilon and you try to find a delta, you won't be able to. In other words, if you went back to the definition. So anyway, that's just a reminder. Okay. Now, that was back when we were young. Just starting out in calculus. We didn't know much. Now we're ready to bump it up and talk about multivariable functions. And now, for example, let me do this. Let me just put in a, whoops, let me put in a page. Okay. Now we've got z equals f of xy. Now we're talking about limits. We're still going to talk about limits. We're still going to say, let's take the limit as xy goes to, let's say, AB. And we're still going to talk about that equaling L, but now we have to figure out, okay, what does that mean? We're still really using our definition of limit. It's still the same thing, but it's a little bit more complex now. Let's suppose that we're talking about this function f of xy. Now, this is going to be a surface. And where you have f of x, you're looking down at the x-axis and for the values to plug in. So you give me an epsilon neighborhood on the y, I'll find a delta neighborhood on the x. Well, it's a little more complex here because we don't just have just one number. So look at this. Let's look at the xy axis. And let's make a little circle here. Okay. And I will say, and here in the middle of this circle is AB, right there. Now, this is a little circle here, and all around this circle, you have values. You have x1, y1, x2, y2, a whole bunch of values in there. But what we're doing is we are coming, whoops, what we're doing, we're talking about the limit. The limit as xy goes to AB. Now, with single variable, we can either come from the left or right. Okay, but not this one. We can approach this way, this way, this way, this way, this way. There are literally infinite number of ways that we can approach AB. Okay. Now, if any one of those approaches is different from the others, then the limit does not exist. Y'all see that? So in other words, instead of a left and right interval, you have a circle. You can think of it as a circle, a disk, okay? So what we would say is, what this means here is this means for all epsilon greater than 0, there exists a delta greater than 0, such that, okay, such that. Now, think about this down here. Here's a point xy, and I'm going to talk about the distance here, okay? See that distance? Okay, that distance has got to be, so here we go x minus a, okay? If that happens, where, now I left off one important part. This length right here, this is a delta, okay? Think about this circle of radius delta. In other words, for every epsilon I choose, okay? So if this is true, then, so I'd say if this, then f of xy minus L is less than epsilon. In other words, no matter how I box in the difference between f of x, no matter what epsilon neighborhood I choose, okay, for z, no matter how I box in z, I can go down on the xy plane and find a circle of radius delta, and every point in that circle will give me a point up there within the epsilon neighborhood. Y'all see that? Okay. Any questions about that? Now, the most important thing to remember is you've got an infinite number of ways to approach this. In other words, there are infinite number of ways that xy can approach AB, and they all have to be the same. Okay? So there's not just a left-hand limit and a right-hand limit. Any questions? Okay, now, just some terminology here. And here's the definition. I just put it in your notes so that you could have it. This right here is said to be an open disk, this first thing, okay? Whoops, okay? This right here is an open disk of radius delta. So this is just going back, kind of defining some terms. And when you say an open disk, it means it doesn't contain the boundary. In other words, it doesn't actually contain the circular dotted part of this. We say a point is in the interior of that disk if this is true. If we can find any circle to draw around that point, and all the points within that circle are within this disk. Okay? You see what I mean? So we pick a point here. Well, I can draw a circle around that, and all the points in there are in the disk. Now, we would say that a point is on the boundary if for every circle we draw around that point, part of the points are on the outside and part of the points are on the inside. Then we say, okay, that's boundary. Now, of course, it's on the exterior, then we can find, well, that's not the interior of the boundary. Okay. Does everybody see that? So if you look at this thing right here, this is a region, and you have an interior point. Notice it's an interior point because I can find a circle to draw around it, and every point within that circle is also within the region. This one, this is the boundary because no matter what, every circle we draw is going to have points outside and inside the region. Now, if we bump it up a notch, now, and by the way, here is just a formal writing out of the definition of a limit. And what I've done here is I've included a picture so that you'll have that. But notice we also have we can go up a dimension. So we can have a function f of x, y, z. If we go up a dimension, then you're not going to have this thing exactly the way it is here. You're not going to have this. It's going to have x minus x naught squared plus y minus y naught squared plus z minus z naught squared. Okay, so instead of a circle, it's going to be one of these things, a sphere. Okay, so what I said about circles up here, an open disk, you could say the same thing about open spheres if you go up a dimension. So every point, if this is an open sphere, or if this is a sphere, an interior point is a point inside that sphere, so that every sphere you draw around that, you can find a sphere to draw around that point where every point is inside that sphere. Okay? If it's on the interior, every sphere you draw around it has points on the outside and inside. Okay, that's intuitive, right? Everybody see that? Okay, now, so how do we evaluate limits? I've written some limits here to help you to see what the procedure would be. Now, remember in Cal 1, evaluating limits a lot of times is really easy. Now, if you look at this first one, there's no reason to think that this limit wouldn't exist. I mean, and by the way, this is a polynomial, okay? X squared y plus 2x plus y squared. And I didn't mention this when I talked about higher order or functions of several variables, but a polynomial is going to be a sum of terms like this, of this form, where n and m are natural numbers, 1, 2, 3, 4, 5, and so forth, and c is a real number. So if we have a sum of terms like this, then we talk about that being a polynomial. So this here is a polynomial. And remember, with polynomials, you can just plug in, okay? And that's the first thing we think about. I'm just going to try to plug in here. So this is 3 squared times 1 plus 2 times 3 plus 1. Okay, so that's going to be 9. There's 15 and what is that, 16? Okay, so just 16. Super easy. This next one, we try to plug in and we get 0 over 0. So remember what we did in the past, we would say, well, I can factor this, x minus y, x plus y, and plug in there and you get 2. And this happens to be a plane, okay? So there's no reason to think that would be, that limit wouldn't exist. If you look at the graph of it, it's just going to be a plane z equals x plus y. Okay, now let's look at this one. Now we try to plug in and we get 0 over 0, and there's nothing we can do with this as far as simplifying it, factoring, canceling, nothing. So we suspect that perhaps this limit doesn't exist. And the way we show that it doesn't exist is we just have to find at least one path that differs from a different path. We need to find one limit. You take this path, you get to a different place than if you take another path. So let's think about paths you could take to get to 0, 0. Well, you could go along the x-axis. Just let y be 0. In other words, this is a path along the x-axis. So let's see where we end up when we go along the x-axis. Well, when we go along the x-axis, let's see what we have. We have, okay, so let me do this. So we have 0, well, let me see here, x squared minus 0. And then down here, we have x squared plus 0. Well, that's just 1. So when we go along the x-axis, we get a limit of 1. Okay, well, now let's go along the y equals, let's go along the y-axis. Along the y-axis. Okay, if we go along the y-axis, let's see what we've got. Well, x equals 0, we're going to get x is 0 now, right? 0 minus y squared over 0 plus y squared, and that's negative 1. Ah, different. If I go along the y-axis, okay, in other words, if my path is along the y-axis, I'm going to get negative 1. If it's along the x-axis, I get 1. These are different. We end up at different places depending on how we approach this point 0, 0. Okay, everybody see that? Now we're done. All we had to do was show two paths don't match. So that one is finished. Now I'm going to explore it a little more, but I don't have to. In other words, whoops, I turned that upside down. Okay, now I'm just gonna play around with this a little bit. Now let's suppose that both of those paths had been 1. That would just mean, okay, two paths take us to the same place, but it doesn't mean that that limit exists. Now, let's suppose that I approach along the line y equals mx. Okay? In other words, there is a line that passes through 0, 0, and it's of that form, y equals mx. I'm going to approach the graph this way. Well, let's see what happens then. I get x squared minus m squared x squared over x squared plus m squared x squared. Okay? That's if I replace the y's with mx. So I'm taking a different path now. Well, if I take that path, let's see what I get. Factor out the x squared on top, factor out the x squared on the bottom, and these cancel, and I get this. I get 1 minus m squared over 1 plus m squared. So apparently, the limit is depending on which path I choose, what the slope is. Okay? So if I choose my slope to be 5, it's going to be different than if I choose my slope to be 1 or 2, something like that. You see what I mean? So once again, we confirm that the limit doesn't exist. Now, there's a lot of things. We can choose any path we want as long as it passes through this 0, 0. We could do y equals x squared if we want it. We could say, let's travel along that path. There's lots of different ones. Okay, now, let's look at this one. Okay. Now, I just have to, so I'm just thinking here, and I don't really know, I don't remember what the best choice of paths, but I can see that if I let y be 0, I'm going to get the same thing as if I let x be 0, right? So if I look at the path along the x-axis or along the y-axis, I'm going to get 0, so there's no point in that. So maybe I'll do this. Maybe I'll say, well, let's approach along y equals mx. We'll just try this, see if it works. I don't know if it will, but we'll just try it. And y equals mx, that contains that point 0, 0. So let's see what we get. We get x squared mx over x to the fourth plus m squared x squared. Okay, I don't know how this is going to work. Let's see what we get though. We get x cubed over m over x to the fourth plus m squared x squared. And let's see if that helps us at all. I've got x cubed m over x squared plus m squared. And really, that's not going to help us, is it? We've still got all these x's in there. I mean, what we would get is we get xm over x squared plus m squared. And that really doesn't help us because we still got x's in the mix. So let's do this. Let's try this. What about if we say y equals, what do you want to try? What do you think would be a good one? Y equals x squared, maybe. Let's try that one. I don't know. So a lot of it, you're just playing around with it. So look, here's what we got. We've got x squared times x squared. Good. Over x to the fourth plus x to the fourth, right? Is that right? That's good. Now we've got x to the fourth over x to the fourth plus x to the fourth. That is x to the fourth over 2x to the fourth, which is 1/2. So apparently that's going to be the limit. In other words, if we approach on that parabola, y equals x squared, we get 1/2. Y'all see that? Okay, so finally, we've got something we can work with there. Now I know this, if I approach along the path y equals 0, I get this. I get, x squared times 0 over x to the fourth plus 0, and that is 0. So if I approach along the path y equals 0, it's different than if I approach along the path y equals x squared. So I say the limit does not exist. Everybody see that? So notice how we did this. We just played around with it. Said, I just got to find a path. I'm just looking for my path. Okay, let's try this one. Now, this one, for one thing, we're not approaching 0, 0. Whatever we choose, the path that we choose, it must pass through this point right there. It has to. Or else we've chosen a path that isn't even going to go through that point. So now, this is in space. This is, it's three-dimensional here. So what we can do is this. We can say, okay, I'm going to pick a point of a line in space that passes through that point. So here's what we do. This is a trick here. I'm going to say my vector is going to be ABC. And I want my line to pass through that point. So it's going to be x is equal to AT plus 1. Okay. Y is equal to BT plus 2. And Z is equal to CT minus 1. Okay, everybody see that? That line will guarantee it's going to pass through that point 1, 2, negative 1. So I'm going to say, okay, if I'm along this path, the path of this line, what do I get? Well, let's see here. I'm going to have up top AT plus 1 plus BT plus 2 plus 3 times CT minus 1. And all that cubed. An extra, all that cubed. Now let's see down here. Down here we've got x minus 1, so that's AT plus 1 minus 1. Okay. This is BT plus 2 minus 2. And then CT minus 1 plus 1. Okay, so you see how that all turns out. Now let's see what we've got here. Up top, well, I've got AT plus BT plus 3CT. Now let's see what this is going to be. We've got, well, that's it, right? See, because the 1, the 2, that is 3, and then we have a negative 3. And then down here, we've got AT times BT times CT. Okay, does everybody see that? Okay. Well, this is looking promising because what we have up top, let me factor out a t. This is going to be a t cubed times a plus b plus 3c cubed. Okay, everybody see that? Just a little algebra. Then this cancels. Now I've got this, a plus b plus 3c cubed over abc. Well, my limit then depends on the path I choose. In other words, my limit depends on this vector. I just said it's ABC. So no matter what I choose for the vector, okay, it's going to give me a different limit. Okay. Any questions about that? Okay, so this one here, it's a little bit tricky, but we need to find two paths where this thing has a different limit. So one of the things I want to do is I think I just want to use my algebra, get it factored. And that means, grouping. So I can group the top, xy minus 2x minus y plus 2. And down here, I'm going to group things together. In other words, the whole purpose for this problem is just to show you a trick that sometimes you can use. Sometimes you have to go back, and it's helpful if you pull in your algebra skills to simplify the thing first. Now, I'm going to factor the top and the bottom, and I'm going to factor the top just by grouping. Notice I've got the x, and I've got y minus 2, and I've got y minus 2 here. So I just factored these two. Down here, I'm going to complete the square. So I take half of this and square it. I got to also subtract off, right? Subtract off 1. And then I'm going to take the y's. So here's what we've got. Y squared minus 4y, half of that, and square it. I'm going to subtract off the 4, and I've got this 5 on the end. So you can see this is kind of a fake problem, right? It works out too nicely. Okay, so now here's what we've got. We've got the limit. It's x, y goes to 1, 2. And then up here, I've got y minus 2 times x minus 1. And then down here, I can factor this, x minus 1 squared plus y minus 2 squared. And then that's it. The 5 is gone. Now, I can say, okay, my path is going to be an equation of a line that passes through that point. Y minus y naught equals m times x minus x naught. Now, every time I see a y minus 2, I can replace it with m times x minus 1. So I've got m times x minus 1 times x minus 1. Okay. Down here, I've got x minus 1 squared plus m squared x minus 1 squared, right? Is that right? Yeah, okay. Now, I guess, let's see here. What did oh, here it goes. Okay. Got lost there for a minute. Now I've got m times x minus 1 squared. And down here, I factor out the x minus 1 squared. And I've got 1 plus m squared. Those cancel. And now this limit, if I go along that path, my limit depends on m over 1 plus m squared. In other words, it depends on the slope I choose. Okay. Now, I want to do this next problem because there was some, there's some questions about it. And this is one that just doesn't jump out at you as obvious necessarily. So on your page, this is F. So we've got 3xy over 5x to the fourth plus 2y to the fourth. Okay. Now, so when I was first asked about this, I was thinking, I wonder. But if you think about it, if you think about this path, y equals mx, let's see what you get. You get 3x mx over 5, x to the fourth, plus 2 m to the fourth, x to the fourth, right? Okay. Now, if you look further at this, this is going to be 3x squared m over, let me factor out a x to the fourth. Just, I don't know. You don't need to, but then you've got 5 plus 2m to the fourth. Now, these x's cancel, well, the ones on top do, and you get 3m over x squared times 5 plus 2m to the fourth. Now, here's the deal. If you choose the path where m is positive, you get infinity, right? I mean, infinity, because this down here, the bottom goes to 0. So if m is positive, then the limit is infinity. Do y'all see that? Because the bottom is going to 0 and the top is constant. Now, if m is less than 0, then you got negative infinity. Now, when I first saw this, I was thinking, well, just choose the path y equals x and then y equals negative x. But then, you can see this is a little more elegant, right? Because you can just choose the slope. So anyway, that was kind of a challenging one. And part of the reason it was a challenge because I didn't make clear to you that you could end up with an x and have the limit to infinity. Okay, so I made it appear that the x's had to go away all the time. So that's where the confusion came on this one.